about the energy efficient digital transmitter design for ingestible applications. So Dr. Yao Hong Liu received his PhD degree from National Taiwan University in 2009. He was with Terax and Mobile Devices Taiwan from 2002 to 2010, working in Bluetooth, Wi-Fi, cellular, wireless SOC products. 2010, he joined IMAC, the Netherlands. His current position is principal membership of technical staff. He's leading the development of the ultra-low power RFIC design. His research focuses on the energy efficient wireless transceiver and radar for IoT and health care applications. He currently serves as a TPC for the ISSCC and RFIC Symposium. So, please.
Yeah, thanks, Chairman, for the introduction. Can you hear me? Hello? Something. Yeah. Okay. So I hope you enjoy the coffee break. Today I'm going to talk about, give a tutorial about the digital transmitter design for ingestible applications. Interesting is that a few months ago I also gave a similar presentation in TU Delft. At the time, the chairman also put my presentation about the end of the day, and also similar to today, it's also a pretty late presentation. I was wondering that maybe because my presentation has something that might reduce the appetite of the audience during lunch and coffee break, so they decide to put me at the end of the day, so the audience can enjoy the coffee break. Yeah. This morning, the presenter Amin, he also present the so-called Nyquist health system. In principle, there are three types of Nyquist health system: wearable, ingestible, and implantable. So the requirement of these three type of system are quite different. So today I'm going to focus more on ingestible applications. So this is the outline. So first I'm going to give a bit introduction about common digestive disorder and also the wireless capsule system for the diagnosis. And the second part, I'm going to dive a bit deeper to the wireless design requirement for this kind of wireless capsule. And then I will have two case studies, one on digital transmit design, and the second one is about antenna impedance tuning and also the detection. And finally, I will have a summary. Okay, so roughly 1/3 of the world population suffers from the chronic digestive disorder. In US, 60 to 70 million Americans, they also have affected by this digestive disorder each year. And there are many different type of, there are quite some digestive disorder that influence the daily life. For example, the common ones like a reflux, meaning the food coming back from the stomach. Also, like a stomach ulcer, that like a hole inside your stomach, that could also lead to a complication like bleeding or cancer. And roughly 10 to 15% of the population has this kind of issue. And the diagnosis of digestive disorder is quite difficult for two reasons. One, it's quite related to food and stress level. So sometimes you have that, sometimes you don't have that. And the second reason is that to accurate diagnose this digestive disease require somehow a bit invasive approach. Okay, now I'm going to switch a bit the direction to talk about gut bacteria. There's a bacteria called Helicobacter pylori. I guess not many people heard about this bacteria before, but this kind of bacteria, they coexist with human for thousands of years. And typically, when the bacteria are inside the stomach, it's difficult to survive because a strong stomach acid can kill all of them, most of them. But this kind of bacteria, they have something special. They have an enzyme that can be converted into ammonia, and this ammonia neutralizes the stomach acid such that they can survive in the stomach environment. But also at the same time, they damage the mucus layer of the stomach, and they can cause some problem. For example, ulcers. Yeah. Maybe most of you might think, well, I don't think I have that. This is something not for me. I'm quite healthy. But you will be surprised. Actually, from the survey of the Center of Disease Control, they make a study about a population, a percentage of population that having this kind of bacteria inside the stomach. You will see actually it's almost like 2/3 of world population has this kind of bacteria. And you can also see that usually the infection rate is higher in developing country than the developed country. But there's also exception. For example, in Japan, although they have a quite mature healthcare system, their infection rate are still quite high. And you can also see, especially like East Europe, Russia, South Africa, almost 70% of the population has this kind of bacteria. And they are responsible for many digestive disorder. And some doctor even say only dead H. pylori are good H. pylori. On the other hand, some scientists also say that because this kind of bacteria has coexisted with human beings for thousands of years, we cannot kill all of them. Otherwise, you also some other complication, for example, allergy. That's also one reason of the lack of this kind of bacteria. So anyway, the scientific community is now still studying this bacteria. What I want to talk about is the gut disorder that is caused by this bacteria H. pylori. So the one that is very common, 10 to 15% of the population that has it is the this peptic ulcer. That means there's a hole on the wall of your stomach. Yeah. And this can cause a lot of uncomfortable feeling for your gut. Even worse, they can cause to bleeding or even cancer. Yeah. And to accurate diagnose ulcer is also a quite oftenly used conventional endoscopy method. And endoscopy is a long, thin, flexible tube that has one side has a light source and also the camera, and then doctor will put that inside through the mouth, sometimes through mouth, sometimes from the other end of the digestive tract, and then they will look at the image of your digestive tract, and sometimes will take samples as well. This kind of method has the also limitations. For example, you need to perform such kind of diagnosis inside the hospital with doctors, so it's quite expensive. Second is that usually this kind of diagnosis is one-time diagnosis, so you cannot do that over the longer period of time, and also it's quite painful. You don't want to do it every day. Also, that it's difficult to reach certain part of the digestive tract, for example, small intestine. And finally, if not careful, there's a rare chance that this endoscopy procedure can damage your digestive tract as well. So from 2001, the FDA approved a new device called wireless capsule endoscopy to have a new approach for diagnose the digestive disorder. So it's a small pill, like the size of like this very tiny one, and you swallow it. And usually the patient will wear a belt, and these pills will take the picture along the way going through your digestive tract. And after 1 day or 2 days, then this pill will be drained out of the body. So some people might ask, why do we need to have a wireless function for these pills? Why not just save all of the image with the internal memory, and then when it's go out, then you just retrieve those data. But the problem is that you don't know exactly when this pill is coming out. And even when it's coming out, it's quite difficult for the patient to get that outside hospital environment. So usually it's without question that these pills usually designed with wireless function. And it's also very useful for certain diagnoses. For example, if you have unexpected stomach bleeding, then it's quite useful tools to diagnose them. Second is that if you have, for example, tumors inside the small intestine, it's also a tool that cannot be easily done with conventional endoscopy. So IMEC recognize there's quite some research opportunity in this domain. So a few months ago, my colleague Chris Van Hoff, they make a nice video to advertise that IMEC's research roadmap in this direction, and I cannot resist to show.
IMEC is working on the first sensor to measure these important digestive processes in real time. Small enough to swallow and packed with technology.
Yeah, so I like the fancy videos. I watched several times and I still like it. Yeah. So now I'm going to the second part about the more wireless design for this wireless capsule system. So this small pill is actually a miniaturized sensor system, and typically they have several key components. First one is sensors for sure, because for capsule endoscopy, the sensor is image sensor, but it could be also other type of sensor, for example, pH sensor, temperature sensor, pressure sensor. It could also be possible. Signal processing, so the sensor will collect the data, and then after processing, they will send out through the wireless units. Power, the energy source typically is a battery, because this device will only stay inside your body like a few days, so typically it's battery powered. Wireless communication, in my opinion, this part is quite critical, because the wireless part will determine the overall size and also sensor quality of the these small pills. I will cover a bit in a few minutes. Yeah. So nowadays we already have lots of miniaturized wearable devices that has miniaturized electronics. For example, our smartwatch or health patch. To design electronics for this kind of ingestible application, we need to even make the electronics smaller. And that also means the power consumption should be even lower. In addition, if you look at the cost, nowadays, if you are an RF designer, sometimes RF designer for a low power IoT application, sometimes is quite frustrated, because like Bluetooth technology chipset only costs like $1, and it's also almost become commodity. But if you look at this is one cost breakdown that I found it on the internet for a smart pills. It's quite encouraging to see that actually the wireless transceiver, including antenna, are the second most expensive component. So that means there are still quite some opportunity there. Yeah. And there are mainly two types of wireless technology for this endoscopy, wireless endoscopy system. One is the EM base, which are based on EM radiation. Second is the human body communication that use human tissue as a media. They have a pros and cons for both of them. For EM radiation base, typically, as we know, that require a big antenna, and this big antenna is difficult to fit into the size of pills. Of course, the good side is that it can reach a longer distance, so you don't need to really the receiver does not need to really close to the body, and you can still receive the signal. Another type of communication is human body communication that does not require antenna, but you do need to have a very good contact with the body. So that also means it will be quite sensitive to the body contact. Yeah. And so far, the mainstream off-the-shelf wireless capsule system still use EM-based approach. And here I would like to show you two off-the-shelf wireless capsules. So the first one on the left one is the most common called POCam. It's from Medtronics, and this pills has roughly like more than 50% of market share of the wireless capsule system. And their communication approach is based on MICS band, 400 megahertz MICS band. There's also another one that is newer called Microcam from a Korean company, Intermedic, and then they are using the body channel communication as a wireless transmission approach. And when you get the data sheet of the capsule, wireless capsule, you will get this kind of lots of parameters. For example, like resolution, that means the image quality. Also, field of view, that means how wide the camera is going to cover. The wider the field of view, that means you need more cameras. Battery life, that means how long this battery is going to sustain the pills. Frame rate, they will determine how fast you take the picture. For some part that flow faster, for example, esophagus here, flowing quite fast, and then usually that require much higher frame rate than the frame rate in the stomach. Yeah. And finally, is the volume. Typically, is like this size, 1 centimeter times 2 centimeter. Yeah. So now I would like to talk about the battery the power consumption requirements. So typically, this pills is powered by the battery, and this kind of tiny battery usually has quite high internal resistors. So that means your peak current of the electronics is limited to few milliamp. And typically, for most of the cases, the peak current is actually consumed by the wireless part because you want to do the transmission and you have PA and you're starting to drain a current. So, this wireless part somehow also influence the choice of the battery size. And the second part is the RF throughput, and they will also influence the image quality. So on the left side, I show you a picture. That is a picture that this kind of camera, when you swallow it, it will take the picture. And that's a picture that is going to be recorded by this device. And here I assume that if we have a wireless data rate of 2 megabit per second, you will get this kind of image. Not so high quality, but if you have a much higher data rate, you could get a better image quality, and they also help the doctor to identify which part of the your stomach has some strange situation. Yeah. So so typically off-the-shelf RF transmitter for this capsule system has a data rate in order of 1, 2, 3 megabit per second. In case you want to get a better image quality or wider field of view, meaning more cameras image, or faster frame rate, then higher transmitter data rate is required for this system. Optimum operation frequency. So a lot of scientific scientists are looking for what is optimum operation frequency for the this kind of pill. When you swallow it and it's going to transmit out, what is optimum frequency? It's actually a very complicated question and has a many factors that influence that. First one is the size of subject. That means how big is the patient, and also the size of antenna, the type of tissues all influence the optimum frequency choice. In this paper, they have done some research, try to analyze the loss versus the distance below the skin in terms of 3 different frequency: 400 megahertz, 900 megahertz, and 2.4 gigahertz. And you can see the higher the frequency, the higher loss can be. So it's roughly like when you double the frequency, you roughly get like 20 dB extra loss. So most of the smart pills operate at the frequency below 1 gigahertz, typically is somewhere close to 400 megahertz. So now it's a problem because the antenna is also a component that is related to the frequency. So on one hand, we want to be low tissue attenuation, so that's why we operate at a low frequency. On the other hand, the low frequency, you have a longer wavelength. For example, at 400 megahertz in the air, you will get a half lambda of a 37 centimeter. And if you want to pack this antenna inside this kind of form factor, that means you might have a small, electrically small antenna. And we all know from the textbook, electrically small antenna typically has poor radiation efficiency and also very high quality factor. And if you have a high quality factor, that means it's very sensitive to the surrounding environment. And I can show you from one example in this paper is that they are designing a tiny antenna inside the smart pills. And then although they already did quite a lot of things, try to minimize the influence from the surrounding, you can see that when they place a battery or without a battery, it's already causing a bit S11 shift. If you place inside the body with different tissue, that cause even bigger variation. So that's why most of the wireless capsule system, transceiver design, they will have a tunable metric network, ensure that your antenna impedance is set in the optimum environment when it's inside the body. Okay, now I'm going to share a bit my view in the future trends for this wireless capsule system that I see from a few literature. So first one is the further miniaturization. So nowadays, this kind of pill has a size that for adult male could easily swallow it, but for sometimes for the female that is a bit small, or for kids, it's very difficult to swallow it. So the future miniaturization is needed. That put also quite some challenge for the electronics design. And the second part is the location awareness. When you swallow it, it can flow quite fast in the digestive tract. And it's good that this pill can tell you, okay, now I'm in the esophagus, or in the stomach, or small intestine, or large intestine. So this should be providing such information. And the third one, which is also I think is a very interesting one, is that a lot of research trying to make the pills stay in certain spot of your digestive tract as long as possible. So for example, there's a interesting recent research work from MIT. They have a crazy idea that they have these kind of pills. So before you swallow it, they will fold it. And then when you swallow it, and these pills, when they're in contact with stomach fluid, it will start to expand his arms. When they expand his arm, it will stuck inside your stomach. So you can stay, this pill can stay inside your stomach for a bit longer time. Like in their research, they stay there for like 15 days. And then after certain period of time, they will dissolve itself, and then the arm will fall off. Then it will go out of the stomach. So this kind of device is also, this kind of idea is also, I think in the future there will be more and more. And finally, that I found it personally interesting is that I hear more and more interest about using Bluetooth as a communication approach. In the earlier slides, we already discussed 2.4 gigahertz is probably not a good frequency for operating inside the body because 2.4 gigahertz has lots of loss. But we also have a huge benefit is that everybody has a cell phone, and cell phones speak Bluetooth technology. So if these pills can also use Bluetooth as a communication platform, can use a communication with Bluetooth, then in principle they are we can open a lot of new opportunity. Here I also want to share again another video that talk about our vision that this kind of a device can be used for nutrition coaching. So,
and they're also perfect for the preventative inspection of our eating habits. Here, the sensor works as a pill you take with your meal. After ingestion, the sensor finds its way through the digestive system. The data it collects tells you how much nutrients your body really absorbs, making individual nutritional coaching a possibility.
Yeah, so this is something that we envision in the future, that we will have more and more this kind of pills that you can swallow, and then that could help you to do the
And they're also
nutrition coaching. Yeah. Okay, now I'm going to go to the second part of my tutorial, which will be a bit boring compared to the first part. It's about case studies, about two topics that I think is critical for this kind of wireless device. So one is the very energy efficient transmitter design, and the second part is about antenna impedance tuning. So in this slide, I compare few popular low power transmitter architecture. On the left side, you see a very conventional IQ based Cartesian transmitter. On the right side is the polar transmitter. And in the polar transmitter, we can further split into two types. One is analog version, another one digital version. So for the Cartesian transmitter, usually it has it can cover very wide signal bandwidth. That's why most of the Wi-Fi transmitter nowadays usually choose the Cartesian transmitter because of the bandwidth requirements. But usually it has a higher power consumption because you can see a lot of components needed: DAC, low-pass filter, mixer, and also very important is that it requires a linear power amplifier, and linear power amplifier usually has a poor efficiency. It has a trade-off with efficiency. And also it has many impairments like IQ mismatch between quantum LO, phase mismatch, gain mismatch between the I and Q passes, and also the DC offset in the signal chain can also introduce the LO feed through. So those are quite difficult to handle in the Cartesian transmitter. On the other hand, the polar transmitter is a very efficient architecture. So we get rid of, in principle, most of the analog components, DAC, low-pass filter, mixer. Now we just modulate the phase information with the PLL and amplitude information with power amplifier. And also this power amplifier can be a switching power amplifier, and switching power amplifier usually has much better efficiency than the linear power amplifier. It has a drawback because the polar transmitter, polar signal, when you convert from Cartesian to polar domain, the signal bandwidth will expand several times. So it's difficult for the polar transmitter to cover very wide signal bandwidth. And usually you would need to do something special in order to expand the bandwidth of polar transmitter. For example, in the amplitude pass, you can only use open loop modulation, although you might have some issue with the linearity. And for the phase part, phase modulation part, the PO has some bandwidth limitation. You need to apply two-point injection technique in order to expand the modulation bandwidth. And then there also comes with a price that two-point modulation has a gain mismatch and delay mismatch between two injection points. On top of that, you also have delay mismatch between the phase and amplitude, as I shown here. So now the good thing about the digital polar transmitter is this kind of impairment is not there anymore, because delay is all in the digital domain. You can precisely control, precisely compensate it. For the gain error, you can also use digital PLL to read out the TDC information, phase error information to correct them. So it's a very suitable architecture for the low power applications. There's one downside, is the Albany Mission. So Albany Mission of a digital PLL, you need to take extra care because there's no physical analog filter at the output of the polar transmitter. So you need to make sure that your emission out of band need to be low enough. So I also covered that part in a few slides. Yeah. I would like to show you one research work from our group. We present a fully digital transmitter, polar transmitter that can support OFDM modulation up to 2 megahertz, and the frequency is 900 megahertz, and the data rate can be support up to 15 megabit per second, and yet the power consumption is just a few milliwatt, 7 milliwatt when it's 0 dBm output, and also operate at a very low supply voltage of 1 volt. Here is the architecture of that chest meter. So actually in that work, we try to comply with the IoT Wi-Fi 11H that use OFDM modulation. So here we also use it. We are going to also use it for the digital transmitter in ingestible applications. This is also the first digital polar transmitter that can cover up to megahertz bandwidth OFDM modulation. So here we see a few blocks starting from IQ processor, which converts the IQ data to a polar data. Polar data has the amplitude modulation and the phase modulation. The amplitude modulation is going to this AM processor, and the phase modulation is going to this FM processor. The amplitude information again is modulated through this digital power amplifier, and the phase information is modulated through this digital PLL. Then in this slide, I quickly show you the IQ processor and the FM processor. The IQ processor, here a bit more information. We upsample the data from 2 megahertz up to 32 megahertz. That is our system frequency, and then interpolation filter, and then we do this Cartesian to polar conversion, which is similar to Codic algorithm. Then we have AM data and also PM data. Because this PM data is going to send to the digital PLL, which many look at the frequency modulation. So we convert this PM to FM with this differentiation, and then unwrap to make sure there's no big jump. We do the differentiation, and then also have a sigma delta to make sure that over a long time the quantization noise is not going to accumulate. Okay, now I'm going to talk a bit more about two-point injection, because this is still not so trivial for many people that working on the digital PLL for wideband modulation. So typically the PLL-based transmitter, it has a limited bandwidth because the PLL itself has a low-pass bandwidth, low-pass filter. If you put a signal to the PLL, your output will be low pass. So it's kind of this kind of slow in behavior. In order to speed up the frequency, speed up your transient, you can add another feed-forward path to the DCO, the second point, and then looking at this transfer function is a high pass behavior. So when you add this low pass and high pass, then you can get this like a close to all pass transfer function. Of course, it's not ideal because the gain of the low pass is determined by the PLL, that there's a all in digital domain. But in the, for the second pass, it's going to the VCO, and you can suffer from a lot of PVD variation. So the gain mismatch between these 2 points sometimes will, most of the time will be an issue for this 2-point injection. And also this delay mismatch between 2 of them is also a problem. So here in the digital PL, it's not a big issue if your data rate is not super high. So it's the same thing that you have a low pass pass and a high pass pass, and then in the digital PL they can convert into a all pass transfer function, and then the delay mismatch. You can just use a simple delay, clock delay, to compensate the delay between them, because you know exactly how much delay is going to be in the PL part, digital PL part, and you just compensate that part. And for the gain mismatch, it's also easy to compensate because you know exactly how much phase error is going to be inside the digital PL. You can measure it and then put it into a kind of like a correlator, and then you can find out what is optimum gain that should be set here. So that's usually in the digital PL, this impairment can be fixed easily. So this is the PL that we use to perform frequency modulation. It's the PL that we also present in ICC 2014. It's a dividerless subsampling digital PLL. So in principle, we have this kind of snapshot TDC that downsample the RF, high frequency RF signal to a low frequency signal. So that reduce a lot of time to digital conversion, power consumption for TDC. And also we have a DTC that support fractional operation. So overall, this PL consume only 1 milliwatt, but it achieve still a very good performance. I think in the next presentation, there will be more discussion about DTC-based fractional PL, so I will not go into cover too much. So here is a key, because previously we talked about the all-band emission of the digital polar could be an issue, so we need to take good care of them. So typically, because in the analog polar transmitter at the output you have some filtering that can help to suppress the so-called clock image. When you're sampling system, you have image at your clock frequency. So in the analog PLL, you have a low-pass filter, physical low-pass filter to help you to suppress them. In the digital PLL, a digital transmitter, you don't have that. So one way to alleviate or to reduce the this clock image level is by pushing that as far as possible. So what you can do is that you use a higher frequency to upsample this data. For example, in our case, we use the carrier frequency divided by 4, which is around 200 megahertz. So we upsample from 32 megahertz up to 200 megahertz, and then push that to here. And because with the sync function from the 0 to whole, they can help to suppress already quite a lot. Yeah. And because in this kind of low power system, the output power is low, so as long as you have sufficiently low clock image, you will not violate the all-band emission. Okay, now about some implementation. For the AM part of implementation, we have this AM processor. So first, we upsample the data from 32 megahertz further up to 200 megahertz. And then we have this also delay compensation to compensate the delay mismatch between PM and AM. Then we go into this retimer. This retimer has a function that makes sure that your data is really aligned with the phase modulation signal, so there won't be any glitch happen. And then finally we have PA, and PA is a 6-bit PA with 3-bit MSB with thermometer coded and the LSB with binary coded. And this is switch cap PA structure that we use in this transmitter. So this switch cap PA was introduced roughly 2011 from Professor Jeffrey Wallin's group. And it has an advantage that it's very linear. You don't need to really put like digital pre-dissolution, and it can already pass quite easily pass the spectrum mask. And also it's very efficient. It can operate at low supply voltage. Very important is that its switching behavior suits nicely to the CMOS scaling. Yeah. And in each cells of the switching PA, you have an inverter and a unit capacitor. And through the switching cap operation, you can get the output voltage here roughly is proportional to the number, this small n, which is the number of the cells that you turn on. So you can use this approach to the amplitude modulation. Okay, now I'm going to show you a few measurement results. So one is the digital PLL. So in the digital PLL part, here I just want to show you that our PLL just consume 1 milliwatt, but then we achieve a decent performance, which is is already sufficient for the OFDM modulation. Yeah. And here is the digital PA measurement result. On the left side is the linearity, 6-bit PA linearity. On the right side is the efficiency versus input power. One thing to mention is that typically when you operate this amplitude modulation for OFDM system, you will back up roughly 7 dB. So even during the back off, we still have an efficiency better than 20%. Okay, now we put it together. Phase modulation and amplitude modulation, we put it together to perform OFDM 2 megahertz OFDM 64 QAM modulation. Here's the constellation, and here's EVM. So EVM, we can achieve a minus 28 dB at 0 dB ample power, which is already above, beyond the requirement for the Wi-Fi standards. And also you can see here start to clip. That's because in the digital domain we have a digital clipping. Yeah. Closing spectrum, spectrum mask. We also want to fulfill the spectrum mask requirements. And you can see here with the sigma delta, we suppress the quantization noise. So that make us to have at least like 5 dB margin compared to the spectrum mask from Wi-Fi. And here is the Albany Mission. We use the this retimer retime signal to make sure that the phase signal and aim signal is aligned. So that helps us to get roughly 10 dB improvement on the clock image. There's still quite some other clock image coming from the frequency modulation, which can also be applied the same technique, the upsampling, to get rid of them. Yeah. But overall, this meet the spectrum unwanted emission requirement for the output power of only 0 dBm. Power consumption breakdown. So we have a total 7 milliwatts at 0 dBm. This led us to a best energy efficiency. If we put into the energy efficiency versus output power, we are here. For 0 dBm, we have a close 1 nanojoule per bit energy efficiency, and this can still be further improved because at the time our SATA is limited by the FPGA to have only 2 megahertz data. Yeah. Okay, so this is the transmitter part. So the final part is about the antenna impedance tuning. So I would like to use a case that is with Bluetooth low energy, but similar technique can also be applied into the ingestible wireless system. So Bluetooth is quite widely used in wearable system. And for example, your smartwatch, you have that Bluetooth health patch, also typically use Bluetooth. So the antenna has to reduce the size, and when you reduce size, you have higher quality factor, and that changes a lot. The antenna impedance changes a lot when you contact the body. For example, in here, there's a study showing that this is when your antenna is designed in the air, and when you touch the body, then your antenna impedance shift. Yeah. So this kind of impedance shift, ideally, we should have a impedance tuning circuits to tune it back such that it will not influence the output power of the transmitter. Now, before I go into our proposed approach of the antenna impedance detection, I would like to recap one fundamental phenomenon, fundamental characteristic of the electrical balance. So in this paper, they present a interesting thing called electrical balance. So that means if you have a balance, and if you try to put the impedance, load impedance of at B node and D node the same, then the signal that coupled to this center type of transformer will be 0. So this is called electrical balance. We also try to use the same concept for the impedance detection. So again, we have a transformer, and then also here we load it with a Z optimum. And if this impedance Z antenna prime is the same as the Z optimum, then the voltage we measure here will be 0 due to the PA. So so this can be used for the impedance detection. Here is an equation that we try to derive the relationship between the gamma antenna, which is the impedance here, and also the V detection, which is center tap. If you have this measurement, then you can get the relation of the you can get the information about the antenna impedance at this node. Yeah. But this is still not the information we want, because eventually we want to know what is antenna impedance it is. And also more is that doing the measurement, there's also other non-ideal is added in. So we need to do calibration. This calibration is to perform in order to first make sure that, for example, when you do this measurement, there's a phase mismatch between the pass 1 and pass 2. So we need to know, we need to transform, we have to calibrate out this extra phase delay. Second is that this has a gain. We also want to know what is the gain of this measurement, this voltage measurement. And the third one is that, again, we want to know the relationship between here and here, because this is not eventually the node we want to know. We want to know the impedance there. So what we do is that we propose a calibration impedance. So we first load it here, and then we do the measurement again. We will get a V detection calibration, and then we use this voltage and also this equation. Then we can get actual impedance of antenna at this node. So this is how we calibrate the whole system such that we can get a precise impedance measurement. Some detailed implementation. So this is a test chip. So in order to prove the idea, we also has a test PA. This is a transformer as shown here. It's a 3:3 ratio transformer. And then we use a passive mixer and also the LO signal to read out the voltage here, the complex voltage here. And here is the matching topology. We use like M shape, 2 inductors, 3 tunable capacitor to perform the tuning of the antenna impedance. And here the power consumption of this impedance detection is only 0.8 milliwatts, which is much lower than the actual transceiver power consumption. Chip photo. So just want to show you that actually the area that we use for the impedance detection is very similar to the rest of the chip transceiver area. And the transformer is quite area consuming, but we reuse that as the PA balance. So actually it's not causing extra area. Measurement result. This is a raw data before we do the calibration. So we measure the, we first change the antenna impedance, we change the phase, and also we change the amplitude of the, we change the gamma of the antenna impedance by the low pool system, and we measure the output, IQ complex waveform output. Then you can see actually there's a phase offset, phase shift due to the IQ mixer of 190 degree. So that's why the reason we have to do the calibration. So once we do the calibration, we tune this phase mismatch and also this transformation. We are able to match this 0 degree of antenna impedance to this. We also get the same 0 degree here. So with this, we can know that what is the antenna impedance through this measurement. Here's the coverage in the Smith chart. If we tune this M-shape matching network, we are able to cover this area, which corresponding to a VSWR of 3. That is already quite sufficient coverage for a typical case that if you put the antenna in contact with your body. Okay, now I would like to just make a short summary. So at the beginning, I try to introduce a few common digestive disorder and also this wireless capsule system that can improve the diagnosis of the digestive tract. And the wireless part of this wireless endoscopy, capsule endoscopy, is a critical part of the whole capsule because like antenna size, RF throughput, power consumption, all influence the design of the capsule. And I also show you two critical blocks in this wireless system. One is a digital transmitter. It has a very well-controlled delay characteristic and also very good efficiency. So that makes it a very good choice for the ingestible application. And impedance matching tuning is also a critical block when you design when you have an antenna in this kind of application that might be influenced by the body tissue variation. So this tuning and detection is critical for the wireless transceiver. Yeah. Thank you for your attention. Yeah.